So session 3 is going to start soon, and I'm the chair of this session, Kazuki Yoshizoe from Kyushu University. And we have 3 talks the session, and the first one is by James G. and Michael Thielscher, titled MCTS with Dynamic Depth Minimax. And I believe the speaker is James G. So could you start when you're ready?
Yep. So today I'll be talking about my paper, which is MCTS with dynamic depth minimaxes. So a quick overview of the talk. We'll first take a look at the background and then the motivation for dynamic depth minimax. So by background, I'm referring to the background of MCTS minimax. And for this talk, because we're short on time, I'll assume that people know what MCTS is and what minimax is. And then we'll take a look at some analysis of terminal lines, which will guide us into creating these dynamic depth models. And then we'll do some experiments and look at the conclusions. So in 2014, there was an interesting paper which combined MCTS with minimaxes with alpha beta pruning. And it did it so it could avoid force losses and detect force winds. And this model, hybrid model, could greatly guide the MCTS tree growth in certain situations with many decisive lines of play. So the authors in that paper introduced 3 different hybrid models, and I'll talk about one of them because this is the one I'll be basing my dynamic depth models on. So in MCTS, what you do is you do your selection, and when we encounter a node which meets some criteria, such as visit count, then we will minimax that node, as shown in step 3. And if we find a proven result, we will backpropagate it immediately, so there's no need to keep going with the MCTS simulations. But if we do not find a proven result, we will just keep going with MCTS as usual. So essentially, we're just embedding minimaxes throughout the MCTS search. So now let's talk a bit about dynamic depth minimax. I think, so the original paper used a fixed depth minimax, and I think it achieved very good results, but I think there's some problems with a fixed depth minimax. And that is a minimax is only useful if it finds a proven result. Because if you run a minimax and you cannot find any proven wins or losses, then you return no useful information and you just wasted a lot of computation for no reason. So one thought I had was, what if we dynamically adjust the minimax depth? So we increase the depth when there are many proven results in the current situation in the game, and we decrease the depth when we think there aren't that many, proven results in the current game scenario. So I'm just going to define terminology called terminal line. So essentially, you can think of this as if you make a move and then that position can be solved within the minimax depth, we'll call this a terminal line for our experiments. So the question is, how do we determine if we are in a region with many or few terminal lines? Because this will determine how we adjust our minimax depth. So I just took a look at some simple factors, such as turn number, branching factor, and rollout length, because I thought maybe through these factors, we can kind of gauge how many or how few terminal lines there are. So I analyzed the nature of terminal lines. Here are the experiment setups. And before starting each turn, I measured the number of terminal lines found in that position. So I ran a minimax search, and I chose the depth which would allow me to complete the experiment without taking an unreasonable number of time. And then I'll measure some other factors, such as the branching factor from the root node, which is how many moves there are available in this position, the average rollout length, which was the average of 1,000 random playouts. So this kind of gauges how close we are to the end of the game, I guess. And the turn number, which is just the turn number of the game. Oh, I was meant to delete that slide. So now let's look at the results of the terminal analysis. So basically what these graphs are showing, so I used 4 games, Breakthrough, Catch the Line, Connect 4, and Othello, and these are the games used in the fixed depth minimax hybrid paper. what you're currently seeing is how turn number correlates to number of terminal lines we found. So for example, in breakthrough, we can see that at the start of the game, when the turn number is low, there's not many terminal lines. But then around like turn 20 is when we find the most like terminal lines. So if you were to interpret this at the start of the game, your pieces have not moved yet, and there's not that many decisive lines of play. But then once you get to the mid game, when your pieces are closer together, then there's many more decisive lines of play. For Catch the Lion, so for those who don't know Catch the Lion, it's kind of like a Japanese chess game, like shogi game, but for kids and very simplified. There's a lot of noise. For Connect 4, you can see that the number of decisive lines of play kind of increases throughout the game. And there's like a spike around, moves 3 to move 7. And if you play Connect 4, you will know that at the very start, there are like some certain traps you have to avoid in Connect 4. And in Othello, so Othello is basically a game where you take turns placing pieces down and you try to flip the other player's pieces, and the game ends when the board is filled and whoever has the most pieces wins. So Othello is very interesting because you can see that there's basically no decisive lines of play at the for most of the game. And this makes sense because because the game only ends when the board is filled. At the start, like there's not that many decisive lines that we can detect within our search depth of 10. And so intuitively, as we'll talk about later on, you can see that if we were to have a hybrid model combining MCTS and Minimax, we should not turn on the Minimax at the start or for most of the game, and we should only turn it on near the end. So I'll quickly go through some of the others. This is the results for branching factor. Just for the sake of time, I'm just going to keep going. And these are the results for the average rollout length. So the average rollout length is very similar to the turn number, but I think it's a better representation of the state of the game because some games, they hit the mid game a bit, like maybe in 20 moves. Some games take 40 moves to hit the mid game. So turn number is not a very precise measurement of the game state, but average rollout length, I think, is much more precise. So now we're going to look at some of the results of the experiment. So first, how I set up my experiments was I would determine the strongest fixed depth hybrid model via round robin. So the strongest fixed depth model, I'll use that as the model we'll test our dynamic depth models against. And then afterwards, I would test my dynamic depth models against a standard MCTS solver just to make sure, we're not over tuning. So it's only good against the fixed depth models. And we want to make sure it's strong in general. So just to give you an idea of the models we are testing against, the strongest fixed depth models I determined were these 4 models with these given depths. And the percentage is a win rate against MCTS solver, which is like basically standard MCTS. And you can see the strongest fixed depth models are actually quite strong. So as for creating our dynamic depth models, I just used a very simple formula, which was I basically took the results of our analysis and then I just scaled it down to our minimax depth range. So essentially, we'll just adjust our depth basically like in a 1-to-1 ratio with the results of our analysis. So we'll increase it when we found many decisive lines and we'll decrease it when we found very few decisive lines. So just to refresh our memories, our dynamic depth models, we use the same model as the original paper. The only difference is we adjust the depth in step 3. So we do not always minimax to the fixed depth. We minimax based on the depth we determine. So looking at some results from our turn number, these are how we adjusted. So this is kind of like our dynamic depth models and how we adjusted the depths. So we'll go through some results and maybe look at some interesting ones. So for breakthrough, you can see that we kind of achieved some equal results for when the K is 2, 3, and 4. For Connect 4, we achieve some strong results when K equals to 4. So we achieve a stronger model if we set K equals 4. This is actually quite interesting because it shows that there is some merit to adjusting the minimax depth dynamically, because it means that so the model we're comparing against minimaxes to a depth of 3. And here it's saying that if we minimax to a depth of 4, so if we minimax deeper, but not all the time, only sometimes, then we can actually achieve better results by more efficiently using our computation power. For Catch the Lion, there's a lot of noise, so the results aren't quite as good. For Othello, we achieve strong results, but I think this was to be expected because this game, you can see on the left, like it really benefits from not wasting computation on minimax early on in the game and only turning it on later on when it's going to be useful. For branching factor, these are the dynamic depth models. So for breakthrough, not that many good results. For Connect 4, we achieve very strong results when k equals to 3. And I think it's because, as you can see on the left, like branching factor has a very strong correlation to, I guess, how decisive the game is in Connect 4, which explains why we achieve such strong results. For Catch the Lion, again, there's a lot of noise. For Othello, again, we achieve strong results, but I think it's to be expected because this is like the game where you benefit a lot from adjusting the minimax depth. And for rollout length, so for rollout length, actually, it's quite interesting because if we look at the rollout length for, let's say, breakthrough, you notice that it kind of linearly goes down. So it means as we approach the end of the game, like we find less and less decisive lines of play simply because there's less pieces. If we go back a few slides to the turn number, you'll notice how this one kind of peaks in the middle, whereas this one decreases throughout the game. And it goes back to what I was saying earlier, which is rollout length is a better indicator of like how the game is progressing than turn number, because not every game progresses at the same rate, right? So in breakthrough, we do not achieve that many good results, even though I believe our measurement for route length is actually more precise. And I think the reason is because as we play the game, there's too much variance in the route length. And unless we take multiple measurements to measure the average route length and then determine the dynamic depth we should use, we will not get, like the variance will be too high. But then if we take more measurements during the game, then we'll be using more resources, which might take too long. So it's a case of, it's like, I think we have a more precise measurement, but it's hard to use it during a live game. So Hashline results aren't as good. For Othello, again, I think for this game, you can kind of do any sort of dynamic depth adjustment and achieve quite strong results. So as for an overview of the results, so if we compare our strongest dynamic depth models against our strongest fixed depth models, these are the win rates we achieve. And you can see that in some games like Connect 4 and Othello, we achieve quite strong results when we adjust the minimax depth dynamically. Whereas in some games like Catch the Lion, our heuristics might be a bit too crude. So we do not achieve as strong results against the strongest fixed depth model. But I think the biggest consideration is that the dynamic depth models have potential to improve, I guess, because we can, like, we use quite simple heuristics. It's easy to imagine that you can use more like better heuristics and improve the performance of your dynamic depth models. Whereas the fixed depth models, they're fixed, like their performance will not change. So some ideas for future research, maybe you can combine some factors or even investigate other factors like the number of pieces on the board, or you could try to fine tune the formulas. But I think there is some potential to look into coming up with better depth adjustment algorithms and applying them and seeing if we achieve stronger results. So that's all for my talk. Thank you.
Thank you for the talk, and time for questions. So maybe you could use the Q&A of Zoom, or if you're a panelist, I think you can ask directly, and maybe you could raise hands on Zoom, or yeah, whatever. And so far I don't see any questions. If I'm missing, please someone please let me know. So So I have some. So while waiting for questions, I have some questions I want to clarify. So could you show me the first graph you presented? Probably I missed the actual definition of the y-axis. I mean, so the result of the trends. Yeah, what are the actual y-axis for the first graph, for example? Yeah, this one, for example. How did you calculate the average terminal lines? Maybe I missed the definition. So average terminal lines were the y-axis, right?
Oh, sorry, I was on mute. So I might have left it up because we were short on time, but for the
Mm-hmm.
terminal analysis, I
Mm-hmm.
basically got two standard MCTS models to play each other
Mm-hmm.
for 4 rounds. And for
Mm-hmm.
like the 400 games, and each game I would log the statistics. And
Mm-hmm.
then I would just sum it up and average the statistics. So for example, maybe one game we found that on time 5, we find 5 terminal lines. Another game we see that on time 5, we found 7 terminal lines. Then the average is 6. So
Okay, I see. So the y-axis of the next graph is the average out of 400 games. So it should be maximum of 400.
uh,
Yeah,
yeah,
you mean the yeah, y-axis. Okay, thank you.
yeah. So
Hmm. So I see the interesting trend. And in Othello, there's a little slight bump around 10, 13. That's maybe game ended in a perfect game or something.
what? Oh yeah. So in
Yeah, yeah.
Othello, I think
Mm,
games end when the board is filled, but there are some
mm.
cases where
Yeah,
I
yeah.
believe
Perfect
got
game.
improved.
Like,
Yeah, yeah,
yeah, yeah. By a kind of blunder of one player. Yeah.
yeah.
Thank you. There any questions from the audience?
My question is, how did you implement your results? I would say, uh, did you, I would say, manage to get a higher playing strength
How, sorry,
in
how,
competitions? Yes,
how did I implement my
yes.
results? You mean the code?
No, no, no. Sorry, no. That's also an explanation of the code. I did not ask you like the code. No, I did ask you in, I would say, a competitive game where you played with your program, and did you then achieve better results than before?
Mm, sorry, then before compared to
To than before compared to what you can do with your new technique?
okay, so though I guess the before in this case is the fixed depth model. So the
Yes,
mini MCTS hybrid with fixed depth model.
yes.
And the after is the dynamic depth models. So it achieves stronger results in some cases, but in some other domains, the results or maybe the dynamic depth model adjustments were not as fine-tuned to achieve good results.
Yes, I understand this. So I had no question on, I would say, the precise, I would say, numerical values of your results, because this looks fine. But then, of course, you try to
Oh,
implement.
how? Yeah,
Yes, yes,
yeah. So I played the models against the fixed depth models for I believe 400 games, so 200 on each side. And then I measured the win rates and I discarded the number of draws. So draws were discarded.
yes. And what was the outcome of the number of win rates?
Yeah. So these numbers you see are the win rates.
That's the 54.57%.
Yeah, yeah.
Okay, okay, okay. Then the question is, of course, what happens with Breakthrough and Catch the Lion?
So I think those games are, for example, for Catch the Line, I guess it's like kind of like a shogi game where
Yes,
the people can move back and forth. And
yes.
I think there's a lot of noise because the
Aha.
game range from like maybe 10 turns to like hundreds of turns. So I think you will need some better heuristic to adjust the depth.
I agree, because it's always difficult to find such kind of things. But I would say the results are quite clear, but let me say, what is your advice to a beginning programmer? Now, not a completely beginning programmer, but an advanced programmer who just managed to do his PhD, and then he would like to go to the competition in the Computer Olympiad. So what should he take from you?
On the programming side,
Yes?
don't make your code too complicated. So I over-engineered a bit, and it took quite a long time to get my models to work. Yeah.
Okay, and last question. What was the comment of Mr. Wienans?
What was the comment on?
Now, you said you continued the work by, you started with mentioning Bayer and Wienans, yes?
Oh, yeah.
Keskin bir kokusu var. Bu nasıl?
Sorry?
It was not me, it was not you. It was somebody else.
Oh, okay.
Yes, this one, yes.
Yeah, this one.
Did you have contact with them?
No, I just read their paper.
Yes, okay. No, that answered my question already, yes. Because
Yeah.
I know both persons, and especially Mark Wienans.
I think there's one last question in the Q&A. Yeah.
And we have 2 questions in Q&A session, but I'm afraid that we are out of time. So I really appreciate if you could answer the questions on Zoom. And I also encourage people to ask questions if you couldn't ask because of the time limitations. And thank you very much for the talk. And then let's move on to the second talk of the session by sorry, it's always difficult for me to pronounce the name right. Chu-Hsuan Hsueh and Kokolo Ikeda. Did you prepare the screen sharing? So the second talk is titled, Can we infer move sequences in Go from stone arrangements? And yes, it's working. Okay, perfectly. So yeah, please start when you are ready. And it's in case you don't know, it's from our program chair. Thank you very much for the work.
Sorry, so can you see the screen?
We see the screen and we hear you, yes. Things are working okay.
Oh, okay, thank you. Then I will start the timer.
Yeah, thank you very much.
Okay, so thank you for the introduction. And hello, everyone. My name is Chu-Hsuan. I'm from Japan Advanced Institute of Science and Technology. And I'm going to share my work co-authored with Kokolo Ikeda. And the title is, Can we infer move sequences in Go from stone arrangements? Then I guess most of the audience are curious about the answer. And now I can only say yes and no. Then I will explain more details later. So first, inference means guesses or opinions based on known information. For example, detectives try to infer criminals from pieces of evidence. And doctors try to infer abnormalities from body checks. Inference also takes place in games. A typical example is card games, where sometimes we need to infer the cards on the opponent's hand. Then how about the game of Go? So when seeing such stone arrangement, experienced Go players can usually infer the move sequence, that is, in which order the stones are placed. And we wonder how computers can do this. In this work, we formulate the problem to likelihood maximization and applied a general optimization algorithm called simulated annealing to solve the problem. Then we conduct experiments on 90 by 19 Go opening games. For the problem formulation, first we need to make some assumptions. The first assumption is we assume the likely function of human players' moves is available. So we have some move sequence, and we want to know the likelihood. We decompose it to the probability of playing each move at the corresponding positions. And later we will use a neural network to approximate the probabilities. We further make two assumptions to simplify the problem. We assume the game always starts from empty board. And also we only consider the move sequence without stones being captured. With these two assumptions, the number of moves always equals to the number of stones on the board. So what we need to do is to decide the order of the stones. So again, we want to find the most likely move sequence to be played. And with our assumption, we transform it to another question. So given a stone arrangement, we want to find the move sequence with the highest likelihood. So with some move sequence, we can calculate the likelihood, and some move sequence has higher likelihood than others. But ultimately, we want to know which is the maximum. So the next question becomes how to maximize the likelihood. And in this work, we apply a general stochastic optimization algorithm called simulated annealing. Assume that the x-axis shows the solution space and the y-axis shows the objective function. Our goal is to find the global optimum. First, we need to create an initial solution. And second, we need to evaluate this solution. In the third step, we create a neighbor solution and evaluate it. So if the new solution is better than the old one, we accept the new solution. In some cases, so like here, the new solutions may be worse than the old solution. But in this case, we accept it with some probability. This will help us to have chances to escape from local optimum. Then we repeat steps 3 and 4, and ideally we will find our global optimum. So to apply simulated annealing to our problem, we need 3 functions: solution initialization, evaluation, and neighbor. I will elaborate more later. So first is solution initialization. We propose a greedy method. Starting from the initial position, we start a black stone that has the highest probability to be selected. Then we play this black stone and lead us to the next position. And at this position, we select a white stone with the highest probability and play this move. At the next position, we select one of the remaining black stones, and so on until we use up all of the stones. And actually, we also tried to initialize the solutions randomly, but in our experiment, we found the greedy one is better than the random one. Next, we need to define the evaluation function. Straightforwardly, we want to maximize the likelihood. So we use it in our evaluation function. But more particularly, we use the geometric mean. Then finally, about the neighbor function. In general ideas, the neighbor function should change the solutions slightly so that the good part of the solution can be kept as much as possible. Meanwhile, the neighborhood function should be able to generate diverse solutions so that we have chances to reach to good solutions. And following these ideas, we decide 3 kinds of neighbor functions and mix them. So first, we try to randomly select 2 stones of the same color and swap them. For the second one, we randomly select 2 consecutive stones and move to some other places. The third one randomly select 3 stones of the same color and rotate their order. All of these neighbor functions are designed to keep black and white stones one by another. Okay, so now we are ready to go into the experiment. And first of all, we need to have the likelihood function, and we approximate it by a neural network trained using strong human players games. The neural network take position as input and will give us the probability of playing the moves. And we target on 90 by 90 goal opening games. We use 100 professional games in our experiment. And we included another 100 games from amateurs for comparison. For both cases, we clip the game record at the 20th and the 40th moves. This is to test the scalability of our approach. Regarding the simulated annealing, we use more iterations for longer move sequences. And as seen earlier, the randomness is involved in the optimization. And we run each setting 5 times and pick up the best solution among the 5 trials. In the result, first of all, we want to confirm whether the optimization is well done. And the measurement is used by the matrix will be the geometrical mean of the likelihood. And ideally, we should find out the maximum likelihood and compare our results with the maximum likelihood. But in practice, it is invisible to do so. Instead, we use actual move sequences as our baselines, as shown in the x-axis. Then y-axis depicts the likelihood of the inferred move sequence. So in this plot, if y greater than x means that the inferred move sequence is more likely to be played than the actual sequence. And we can see in some cases, the inferred sequence looks more natural than the actual ones. And in some other cases, the actual sequence has higher likelihood. Then let's see the 4 settings at once. Also, we calculated the regression lines. And from the coefficient of the regression line, we conclude that the optimization was generally well done. So in most cases, the slope is greater than 1. Then the next result, maybe the most important metrics in this paper, maybe. So we wonder how many inferred sequences exactly match the actual move sequences. And here's the result. So in the case of professional games with 20 moves, 51 out of 100 games exactly match the actual games. And when the sequence became longer, the results got worse. And the result was even worse for amateur games. Overall, the matching rate looks low. But wait, did we fail? Well, I want to say no, because when we observe or when we review the inferred sequences and compare it with the actual sequences, we find that some inferred sequences looks more reasonable than the actual ones. So the next matrix, we want to quantify the reasonableness. we use Katako to evaluate each move. So Katako, given a position, will give us the best move and evaluate its territory advantage. We also let Katako evaluate the actual or inferred move's territory advantage. Then we calculate the difference to get the loss of the actual or inferred moves. The loss is the lower the better. And here is the result. Similar to result 1, but this time we plot on the loss instead of the likelihood. So the same, the x-axis shows the actual move sequence and the y-axis shows the inferred sequence. And
Sorry, I think I don't show anything right now. So not sure if the connection's okay.
Anyway, we do not hear anything. I hear you, but I do
I
not
think
hear the speaker. Yes.
I think the speaker's movie is kind of now frozen, so probably our connections now also let's just wait for a minute and hope she returns. And in the worst case, maybe we would ask the third speaker to start the talk, but let's just wait for 1-2 minutes.
Yeah, it's fine for me.
Yeah, thank you very much. Yeah. The timer is still working, so I think that it's not that the network is fully down, but can someone?
I assume at your side the same happens at my side. It stops, I would say, abruptly.
Can someone contact? I mean, is someone close to the speaker physically?
Well, not physically. I just did write an email, but I fear she will not recognize. I mean, she's likely still talking. I'm
afraid. I'm not sure. I think I cannot find someone who's physically close to her right now. Not sure if possible, if could someone make a phone call or a chat or something, but So it's sad. So the talk was sound very interesting. So, but if she doesn't come back in 1 more minute, then I would like to ask the third speaker to start the talk. So, sorry for the trouble. And but I'm not sure if I could forcefully stop the screen sharing.
I can.
Thank you very much.
Stop.
Yeah, thank you very much. Thank you. Yeah, thank you very much. So I'm sorry for that trouble. So, and thank you very much. Well, I would like to ask the third speaker to start screen sharing. It's
Yeah.
Thank you. So the third talk is about Satoru Fujii from Kyoto University. The title is Quantifying Feature Importance of Games and Strategies via Shapley Values. And could you start screen sharing?
Yeah.
Look okay, yes.
I hope screen sharing. Yes, thank you.
Yeah, it works. Okay, yes. So please start when you're ready.
Yeah. I'm Satoru Fujii. Let me present my research, quantifying feature importance of games and strategies via Shapley values. When we play games, we look at features. For example, when we play poker or Texas Hold'em, to be precise, one feature might be our hand, one might be community cards publicly shown in the center, or it might be some of the money in the pot, the money you get when you win. Or bet history might also come in handy to estimate hands of other players. Maybe they're bluffing, though. The question here is, which feature is more important, or how much importance do they have? Thanks to recent advancements, now we have plenty of strong AIs to play games and the means to create them. And yet, we don't know how they think. Well, we do know their inner workings or algorithms, to be precise. It's just we can't interpret or comprehend their strategies. And we believe that knowing which feature is more important for them, how much importance do each feature have, would help us to understand their decisions. We call these values feature importance. Let's point out that these seemingly similar questions actually hold significant difference. The first one aimed to obtain feature importance of games, its importance for the optimal play, and it is to understand the game itself. While the second one aimed to obtain feature importance of strategies, which is importance for a specific strategy, and its purpose is understanding the attention of an AI. Well, it's also possible to think about the same thing for a human player, but here we kind of omit that. Before we get to the specifics of my research, I need to talk about Shapley values. Let's think about the situations where these team members, yellow, blue, and red, cooperated and achieved profit of $600. Shapley value represents how much each member contributed to the result, or in this case, how much share should they claim, how much this $600 should be distributed among team members. Maybe one of them worked so hard and contributed a lot, or maybe some of them are just, slacks. In short, Shapley value is calculated by average marginal contribution among all permutations. For example, this is how to calculate Shapley value of red. Let's assume that when only yellow and blue cooperated, profit would be $300, and then adding red to the table increases another $300. We do the same thing for all permutations, calculating the marginal contribution of red, then averaging them. Note that it's the average of permutations, not combinations. So the top one and the bottom one should be double counted in this case, since the order of yellow and blue has two patterns. In this case, Shapley value of red resulted in $210. Okay. Now we know that what Shapley value is, but what makes it so good that we needed to go through all this trouble just to quantify feature importance? We could just obscure one feature, calculate the difference, and call it feature importance. It's simple and all. But why don't just do that? The thing is, it is known that when applying Shapley value, to features for local AI output, that value is proven to be the only feature importance that satisfies 3 desirable properties, which is local accuracy, the sum of face value, and feature importance equals output. Missingness, importance of relevant feature would result in 0. And consistency, if we change AI so that one feature have more marginal contribution everywhere, the importance of that feature would increase. This is for local feature importance, and using Shapley values for global feature importance is also studied and also known to satisfy similar desirable properties. Now, let me get to the content of my research. It features 2 methods to calculate feature importance, each for games and strategies, correspond to the 2 questions earlier. Shapley game feature importance, which we abbreviate as SG5, and Shapley strategy feature importance, which we abbreviate as SS5. Let's assume that each info set or subjective game state basically can be represented by M handcrafted features. Large M denotes the set of M features, and Fj denotes discrete feature function for each feature J. Firstly, I'll talk about SGFI. We denote set of visible features as S, and this alpha A, S is an abstraction for player A that merges info sets sharing the identical set of actions and feature values of each feature in S. This means information contained in other features are discarded, and hat sigma is approximated Nash equilibrium under an abstraction, which we calculated via an algorithm called Monte Carlo counterfactual rate minimization, or MCTS, in our experiment. And U denotes the expected return. Calculation of SD5 is done by calculate expected returns of equilibrium strategies with abstraction for every possible feature subsets, then calculate marginal contributions of each feature. The trick here is that SGFI is calculated using abstraction only for the target player, meaning the opponent plays in null abstraction. This is because it is known that finer abstraction leads to less exploitable or better strategy in this way, while the same can be said when using abstraction for both players. In our experiment, we used the game called Goose. Well, in short, in each turn, one card is randomly chosen from the deck and publicly revealed in the center. And then both players simultaneously choose one card from their hand. Then the player with higher card claims a point shown in the center card. Cards utilized in each round are then excluded from further play, and after every cards are used, the player with higher total points wins the game. We arranged 4 features to explain each info set of this game. C is the card in the center. D is remaining cards in the deck. And O is the hand of the opponent. And P is the difference of the total points. Note that in Gooseby, the target player's hand, it determines the target player's action set, which is necessary to play this game, so we exclude it from feature set, meaning it is always visible to the target player. This is the result. The graph on the left shows the convergence of the expected returns in MCCFR iterations for some feature subsets. Legends show the elements in the set of visible features. Only the final value, resulting value, is used for SGFI calculation. Well, it can be seen that using more visible features yields better expected returns. The most intuitive heuristics for Gooseby would be choosing higher card when the center card is higher, and sparing higher card when higher cards are remaining in the deck. And relatively, it's not easy to use the information of the opponent hands or points. This is well in accordance with SG5 values shown on the right. We also found that just using the difference between full feature and one feature exclusion, or using the difference between zero feature and one feature abstraction, leads to rather unintuitive outputs, highlighting the merit of using Shapley values for this purpose. Secondly, I'll talk about SS5. Calculation of SS5 for local strategy sigma I on info set I is done by something like this, setting phi0 to be the average strategy over the info sets with same actions, then calculate phi-j SS5 vector of J by averaging the output of the following procedures. And firstly samples info sets I alt with the same action set, and then samples permutation O from every possible permutations. Here, features before J in O is denoted by P, and features after J is denoted by Q. And then, well, this is complicated, but 3 and 4 basically sampling info sets with the same features values of P with a target info set I and the same feature values of Q with I alt. Feature J is the same with the target info set I on 3, while feature J is the same with I alt on 4. And 5, lastly, the difference of strategies between info sets sampled in 3 and 4 is calculated, and the average of them is SS5 vector of feature J. Well, in short, this algorithm randomly samples marginal contribution to the strategy, which itself is already known. In our particular algorithm for this game strategy, feature obscuration is achieved by using random strategy with the same action set and visible features. This is an example of SS5 on Gooseberry yielded by our experiment. One of the good things about this is that the sum of SS5s of each features equals AI output as shown in the table, which greatly helps us to comprehend this with intuition. In conclusion, we proposed SG5. It tells us which feature is more important to win, and it can be utilized to understand the game on macro level. And SS5, it tells us which feature is focused on by an AI, and it can be utilized to decipher the attention of strategies. They yield intuitive explanations that resonate with and augment human understanding. We hope that these methods will enhance human learning supported by AI and streamline collaborative decision-making processes between humans and AI. Thank you for listening. That's all.
Thank you very much for the talk. And now, if there are some questions, please ask by Zoom QA or raising your hands or start talking if you're a panelist. And well, I think I see no questions so far. So may I ask questions while waiting for the questions from the audience? I found it very interesting, but so the first question is that is it possible to extend to more complex games where the number of features are greater, or what is the limitation?
Yeah, well, about for SG5, the calculation cost, well, it just exponentially increases with the increase of the number of features. But I believe that we can just use sampled permutations similar to SS5, we could ease that calculation cost. And about SS5, it's more easier because it doesn't exponentially increase with the increase of feature numbers. It is easier to calculate than SG5. Or for SS5, I think it's fine. I hope this answers.
Yeah, thank you. Yes. So any questions from the audience?
Sorry, I would like to have a question.
Yeah,
please.
Yes. Let me first repeat your title and then my question. So, quantifying feature importance. I understand that it's very important, yes. And strategies. And then you said via Shapley values, yes?
Yes.
That your talk was convincing. So I understand that you did in that field, you did a good job, yes? But now I ask you, what are the alternatives and what are you doing better? What is the improvement for the Shapley values?
My methods versus Shapley values.
Yes, I understand. You explained it very well. So my compliments for that part. And then always we have questions. And then, of course, in questions, you try to, first of all, to broaden the understanding and also to broaden the application. And so that is the background of my question.
The thing is that we kind of use Shapley values to quantify feature importance of games. And we use Shapley values rather than kind of compared with Shapley values. And the thing is that using Shapley values, it's a simple statement, but we believe there are several possible implementations for the game. And in our particular methods, we did that for like using single player abstraction or like using feature abstraction by using random strategy with the same action set and visual features. Like there are also alternatives that use like, neural network AI and use kind of Shapley calculation methods tuned for neural network, which is called Deep Shap. There are a lot of alternatives to calculate Shapley values for games. And it might be better to use that against our methods when you're using like very complex neural net AIs or something like that.
Well, thank you for the answer, but that was not my question I would say, to say to you that your method was not good or that we have better methods. But I like to, I would say, to understand, we have a game, and then you say that game, whether it is chess or shogi or it is Connect 4 or whatever, yes, you see there are features in that game, yes? And I would like to know the importance of that feature for, I would say, for my playing style, and not my playing style, in fact, my playing strategy, because I'm a game player and I would like to win. So I would like to know what is the best strategy I can use. Yes? So how can I make, I would say, the features instrumental for my strategy? And then you use the Shapley values, and I asked you, what is the background of your choosing the Shapley values instead of some other possibility of values?
Okay, I think I understand your question. I'm sorry.
Okay.
And the thing is that in Shapley values, our method, like in Glücksspiel's case, the values importance of center and deck is higher than opponent and points, which is like very intuitive, at least to me. But why there are like other alternatives to calculate quantify feature importance, such as like full feature versus one feature exclusion. It resulted similar importance for all features in this case, and it is not very intuitive in this case. Like the value of center card and cast remaining is a deck, they are more important than opponent's cards or points, at least in our intuition. And their other alternative would be empty feature versus one feature, the difference of them, but it resulted in no importance for opponent and points, and it is quite not right because there are cases where the value of opponent or point should be used to determine the optimal strategy. So this doesn't quantify feature importance in a good way. So Shapley values works better than these two alternatives.
Okay. Thank you. Now I understand better, I would say, your motivation and also your choice. And I wish you much success with exploiting the Shapley values in a further direction and to support your work. I enjoyed very much listening to your talk. Thank you.
Yeah, thank you for the questions. Thank you.
Yeah, thank you. And I think we have used up the 20 minutes time slot for the talk, but in case you have more questions, please use a Zoom QA as I recommended before. So I would like to thank the speaker and please send some kind reactions to the speaker.
Thank you.
And so are you back? Chu-Hsuan, are you back? I see you as a co-host.
Yes, I think.
I feel very sorry for your trouble. I'm not sure how strict should we be about the time schedule, but probably it's up to you. So if you think it's okay, maybe you should just spend some minutes introducing your last part of the talk. And I'm not sure. I think it's you to decide, right? I'm not sure. Should we be so strict about that?
I'm in favor for giving her the opportunity to finish her talk.
You're right. And then we could take some questions during the break or on Zoom. So yeah, please resume from the point you've lost your question. It's about where you started to talk about the category score analysis using to analyze if the sequence is good or not. So
okay. So first of all, I apologize for.
No problem. It's unavoidable, so you don't need to apologize. And really, thank you for your effort for as a co-chair. And yeah, please just resume.
And if audience has other things to do, please feel free to leave.
I stay with you, so I continue. So at least there is one member, but I'm sure there are from the 29 members, there are probably 25 persons, and so four apologize. So I hope that we continue with a good group. Yes.
Yes, and yeah, right here. I think yes.
So this page has been expanded and I disconnected at this page.
Yes, exactly at this point. Yes.
The category. The lower, the better.
Okay, so we found most sequences look more natural. So in some cases, the inferred sequences were more natural than the actual ones. And in this analysis, so the graph on the plot is similar to result one. We plot the actual sequences loss at the x-axis and the infer ones in the y-axis. But this time we see the area of y lower than x. In this case, this means the inferred sequence has lower loss than the actual sequence. So in this case, this means the inverse sequence was better. And we also calculate the regression lines. So from, let's see the result at once. So an interesting finding is that in professional games, generally the inferred sequence were worse than the actual sequences. But for the amateur cases, the infer sequences were generate better than the actual sequences. And we wonder whether sorry, I'm a bit emoted.
Yeah, but thank you very much. I mean, this is I found this talk very interesting. So please just take your time. And
okay, so we asked 3 Go experts to evaluate the inferred and the actual sequences. In the following, I will show 2 examples. The first is from the amateur games. On the left is the inferred sequence, and on the right is the actual sequence. The likelihood and the loss information are also shown. So in terms of both metrics, the inferred sequence looks more better. Then how about the experts' comments? So for the move sequence on the left, the experts comment that the overall stone shape and the direction of territory development is more nature. On the contrary, in the actual games played by amateur, the 15th, 16th, and 20th moves looks strange. So in this case, the infer sequence was indeed more nature and better than the actual sequence. The second example is from professional games. In this case, the first 20 moves are the same. And after white play at this location, it is urgent for both players to play at Q15. This is an urgent point. In the infer sequence, this move is immediately played after the 20th moves. But in the actual sequence, this move was overlooked for several moves. So from this point, the experts think the infer is more nature. And another point is about when to cut in the white territories. So on the left, the infer sequence cut in, try to split the white territory after the enclosure of this white stone. And this is, the order is reversed in the actual sequence. So from these 2 points, the experts also concluded that the infer sequence is more nature. And final recap, so we did Go move sequence inference from stone arrangement. We formulate it as likelihood maximization and use simulated annealing to solve it. And there are some promising future work. And first, we think it will be interesting to ask human players to also do the inference and compare the results. And we want to extend to more complex problems, like longer games or games with stone captures. And we want to try other approaches like transformer, which is known to dealing with sequences data well. But before that, personally, I want to try to apply these methods to infer some stone arrangements in Go comic book, like one very famous in Japan and also in Taiwan is the Hikaru no Go. So this is my second part of presentation. Thank you for your attention.
Thank you very much for the talk. And we have one question on Zoom QA. So I also have the same question. So I think you can read, but in case you cannot see it, why is it important to infer move sequence from stone arrangement? Do you have a real world application in mind? So
yes, actually we have, but I will starting from interesting ones and then practical ones. So interesting ones is One is I just mentioned, we can use it to infer some stone arrangement in comic books or in some TV programs, just for fun. And also we can apply the system to amateurs for their enjoyment. And a more practical one is that, so actually I'm planning to generate Go puzzles for training middle level players. And in this context, we try to analyze the Go puzzle sets, which is commercial and commercially available. And we believe there are many good questions, and we want to analyze which properties those puzzles have. But one thing is that those puzzles usually did not have the sequences, while in our analysis, the sequences is important. So a practical use will be to analyze the Go puzzles in commercial books.
Thank you for the answer. And we have actually two questions, one in QA, the one in the chat. I think you can see both. And yeah, both are interesting. I'm also interested in these, but I'm not sure if we could extend further. So thank you very much for the talk. And I think we have lots of questions from the audience. Please use Zoom chat or Zoom QA to ask, and I appreciate for the speakers if you could answer the question afterwards. And despite the trouble, I'm sorry for the trouble, but thank you very much for the talk. And so this is the end of the session. So I would like to thank all the speakers and all those who participate in the discussion. And please send us some big hands and warm reactions. And sorry for the extension. And this is the end of the section. And I want to, yeah.